Hello, and welcome back to another episode of the Curiosity Monkey podcast. So, you probably noticed that there's quite a dramatic increase in the number of electric vehicles on the roads today compared to 10 years ago. Now, with this increase in the number of electric vehicles, some people are concerned over the risk of fire compared to other vehicles, such as internal combustion engine vehicles. So, in this episode, we're going to be comparing the fire risk of electric vehicles and their batteries with the fire risk of internal combustion engine vehicles. And we'll also be comparing the hazards, so how dangerous each fire is. Also, for electric vehicles and battery fires, we'll be looking at how they start and what kind of causes them. And note, this can be applied to other battery vehicles as well. Say, well, not even just vehicles, but fires that start from your phone, from a laptop, from anything with specifically a lithium-ion battery in this case. But it could be electric scooters, electric bikes, because there have been actually quite a few incidents of fires starting not only in electric cars, but actually in electric bikes and electric scooters. So for this reason, electric scooters are actually banned on many public transports in the UK because of this fire risk. So we'll have a look at what is the risk of fire and what causes it, and how can it be prevented, and also how can you extinguish the fire. So first of all, a brief introduction. I actually did a whole podcast episode probably about a year ago, probably less, probably more than a year ago now actually, on electric vehicles and actual stats to do with them, what makes them good, what makes them bad in some cases. So a quick brief overview of electric vehicles. So electric vehicles are just vehicles powered by electric motors. So battery electric vehicles rely only on the chemical energy from the battery. So the battery is what's powering the vehicle, powering the motor. And you've also got plug-in hybrids and hybrids that both have a battery and use fossil fuel energy to power them. So electric vehicles were invented in the 1800s due to development of battery technology and electric motors. So in fact, they were like one of the first kinds of cars to come around. But EVs were in high demand in the early 1900s for a while due to fuel shortages. But this demand fell as oil became cheap, and so manufacturers decided that internal combustion engine vehicles were the way to go forward. And since then, there's been a lot of investment and development over the last 100 years or more on internal combustion engine vehicles. So that's why they're so prevalent today. And today there are billions of internal combustion engine vehicles on the roads and consuming around 30% of the global energy demand. So it's quite a significant quantity of energy. And for this reason, people are seeking to shift away from relatively inefficient internal combustion engine vehicles because of the climate crisis. So in 2021 today, there's quite a lot more concern for the climate. In fact, 100 years ago, we didn't really have a clue that we could impact the environment around us so strongly. But today, most of us, if you believe in science, are aware that we can impact the environment around us, and we indeed have, by raising carbon dioxide levels in the atmosphere, which has led to a greenhouse effect. So people are tending to buy electric vehicles because over their lifespan they seem to emit less carbon dioxide due to efficiency of power plants. Generating electricity is much greater than that of inside an engine of a vehicle, internal combustion engine vehicle. Even if you take into account energy losses through power cables, and you could still use the dirtiest power source available to you, like dirty coal, and it would still release less carbon dioxide than burning inside an internal combustion engine vehicle. But in the UK, we shifted away from burning coal to generate power to more gas, with of course an increase in renewable energy as well. And burning gas compared to coal, releases much less carbon dioxide per unit of energy. And it's also cleaner in terms of it doesn't release as much particulate matter into the atmosphere, which is pollution. Now, carbon dioxide itself is not pollution, but it is what contributes to the greenhouse effect. And the reason power plants tend to be more efficient than inside a car engine is because they burn at much hotter temperatures and in the presence of much greater oxygen concentrations, allowing complete combustion of the material that's being burnt. So this is one of the major selling points for electric vehicles in terms of the environmental impact. And so governments are also incentivizing people to buy these vehicles, and there's been a massive uptake. In the UK, we've just passed 1.1 million electric vehicles as of June 2024. And this is set to increase significantly in the next few years as the prices continue to fall and the technology keeps getting better and better. So, yeah, electric vehicles are still in the phase of infancy, which means the technology is still advancing quite rapidly at this stage, and prices are falling quite significantly due to economies of scale. So more people are buying these, and the more people who buy them, the cheaper it is to manufacture per unit. Also, the infrastructure and charging to support the use of vehicles, electric vehicles, has increased. So charging stations, fast charging stations are essential if you want people to use them. So getting that infrastructure in place is very important. Also, a quick note that people aren't just buying these vehicles because they're meant to be more environmentally friendly. They're also buying them because the technology has actually improved so significantly that in some cases they are just better than internal combustion engine vehicles. So a recent survey revealed that 91% of electric vehicle drivers in England have no intention of switching back to an internal combustion engine, with 86% saying that they've been cheaper to run, which includes charging them and maintaining them. So I have a whole another episode, as I say, on electric vehicles, benefits and downsides, but they tend to be cheaper to run because electricity costs are lower than that of gasoline, and also they have fewer moving parts, so they tend to wear down less quickly. But with all this information, it's quite clear that electric vehicle uptake is taking off at a rapid pace. And for this reason, it's important we understand and manage any risks that are brought by them. So there have been a few examples of battery fires. So in the media, there have been quite a few stories about electric vehicles and fires. And some people are getting worried about this. So this actual question was sent in by a listener looking at the risk of electric vehicle fires and the hazards of them. So how bad actually are they? So before we actually get into what causes them and how can we extinguish them effectively, we'll look at some statistics on the fire rates in internal combustion engine vehicles and electric vehicles. So there have been a few studies of whether lithium-ion batteries in electric vehicles pose a potential fire hazard, and we'll quickly go through this. One study report concluded that lithium-ion battery fires occur on a somewhat comparable or perhaps slightly lower level than those of internal combustion engine vehicles. And it also said that the fire hazard, so how bad the fire is, for lithium-ion batteries are expected to be a bit less because there's a much smaller amount of flammable solvent within the battery. So we'll come on to what the battery is, what causes the fires within the battery in a bit, so that might be more understandable in a second. But if you think about the sheer volume of fluid, flammable fluid within a regular car, especially when it's full, so it could be like 50 litres or more. My car's quite small, 50 litres it probably holds. However, other studies conducted have suggested that the risk of fire in electric vehicles is actually substantially less. So I think one suggested that the risk of fire within electric vehicles is 20 times less than that of internal combustion engine vehicles. However, there's still a lot of uncertainty in these studies because, well, this one main reason is because the majority of electric vehicles in the world are still relatively new. So as the number of electric vehicles grows rapidly, there's not many older vehicles to look at. So we can't really properly make a fair comparison between the two, whereas there's still a lot of old internal combustion engine vehicles on the road. So the average age of electric vehicles is going to be far younger than the average age of internal combustion engine vehicles on the roads in the UK. However, there are some other statistics we can look at. In Teslas between 2013 and February 2024, there are only 218 car fires confirmed. And taking into account all Teslas, the distances travelled, the number of fires, you can come to the conclusion that one Tesla is involved in a fire incident every 130 million miles driven. And this is between the period of 2012 to 2022. However, in the USA, one internal combustion engine vehicle catches fire for every 19 million miles. So this is a higher rate, much higher rate. But as I say, in reality, there's a lack of statistics, so we can't fully conclude yet. However, it does seem likely that the risk of fire in electric vehicles is at worst comparable to the risk in internal combustion engines. No study I've seen has said it was more, the risk was higher. Every study said it was less or comparable. And I should clarify here what I mean by electric vehicle. In this case, these studies are looking at battery electric vehicles, so these statistics don't take into account plug-in hybrids. And a side note here, that while electric vehicles are not at great danger for fire, it seems that other battery devices may be. So, as I said in the introduction, that there's quite a few fires within electric scooters and electric bikes. And it seems that many of these electric scooters especially are coming from unregulated sources, unregulated markets where the batteries are just not very good. So these batteries may be faulty, just not made very well, or the design could be not very good for what the product's designed to do. So if you think an electric bike and electric scooter has to discharge a fair amount of power because it's got to power a human moving it. So a lot of energy discharged very quickly can cause heating, and if the battery's not designed to do so, it could cause fire. Also, a lot of these fires are caused by incompatible chargers and modifications to these products to make them, say, go faster, or say for an electric bike, you could modify it so you don't even have to pedal for the motor to work. But the reality is that well-made batteries bought from well-regulated markets are very low fire risk. If you think these lithium-ion batteries are on a lot of technology we use today, including the laptop I'm recording this on, phones, pretty much all phones, cameras, loads of technology uses these lithium-ion batteries, but there isn't a massive problem where these batteries are catching fire. Yes, it does happen in some cases. However, in the phone market, there are so many people these days with mobile phones, and we do hear scare stories of mobile phones catching fire and exploding, but because there's so many of them, it's just such a low minority. So as long as you buy your electric bike, especially from a trusted source, where the battery is from the manufacturer, not a third-party one, then it's likely not to be of poor quality. It's just when the battery is A, taken way beyond the manufacturer's specifications for its use, so if it's basically abused beyond what is recommended, or B, if the battery is just very poorly designed for its use, then this is when you run into problems. Because if you think about it, electric car batteries have to deal with so much more power outputs, say rapid transfers of energy to accelerate large masses compared to an electric scooter where you're accelerating much smaller masses. Yet electric scooters seem to be at much greater risk of fire than electric cars. So the batteries found in some electric scooters and e-bikes are of poor quality and do not meet UK safety standards. But For electric bikes especially, bought from established brands and reputable retailers, do seem to pose a very low risk of fire. It does seem to be bikes and batteries that are not from very trusted sources and maybe modified. These are the ones that pose risk. So if you have an electric bike, it's likely not to worry. Just buy your batteries from trusted sources if you need them replaced, and don't modify the bike to make it do anything that it's not designed to do, because that can increase the power output from the battery, which it might not be designed for. But as I say, well-made batteries from well-regulated markets are at very low fire risk. So quickly we'll look at the batteries in electric vehicles. So first of all, why lithium-ion batteries? Well, lithium-ion batteries are used because they're quite good at storing energy. They are energy dense, they are lightweight, and they have quite a long lifespan compared to other battery technology. They're also very good at recharging, so they don't degrade much over each cycle. So as you charge a battery from 0 to 100% and drain it, that's kind of a cycle, and over each cycle you can charge the battery less and less well as it is, and so it degrades less per cycle for lithium-ion batteries compared to many other technologies. And this makes it very good for electric vehicles because, well, you can recharge them. You don't have to replace the batteries very commonly. And also they can output a lot of power, which is required for the acceleration of the large masses of the car or the lorry. And this is why you can get quite these electric cars with very high performance. You just simply wouldn't be able to do that if the battery couldn't output high amounts of energy very quickly. And these batteries are able to recharge very quickly compared to older battery technology, which is just very good if you want electric vehicles, because one of the most commonly cited issues with electric vehicle, people hesitant to get these vehicles, is that they take so long to charge. So what if I want to go 200 miles, 300 miles, then I might need to charge halfway. I don't want to spend 8 hours at a charging station. Well, if you can charge it up in 15 minutes, half an hour, that's going to be game changing. So what is a lithium-ion battery? Well, a lithium-ion battery cell consists of a cathode, which is a negative electrode, and an anode, which is the positive electrode. It also has a separator and an electrolyte. So the cathode is what gives it the name lithium-ion battery. It is made of lithium metal oxide, where the metal is often a transition metal, such as cobalt. The separator is a thin, non-conductive material which sits between the anode and the cathode, and it permits ion transfer, but not electron transfer. So for this, it just prevents short circuits, basically. And the electrolyte is a liquid or a paste that allows the movement of lithium ions between the electrodes. And a typical electrolyte for a lithium-ion battery is made of a flammable carbonate-based organic solvent. And during the discharge of the battery, lithium ions, positive ions, move from the positive anode to the negative cathode. And the cell is where the chemistry happens. And this is where the energy is stored. So the chemical energy within the battery is converted to electricity. So that's the point of the battery, I guess. And so a battery system consists of several batteries. Basically, the battery pack is made up of loads and loads of batteries, which each battery contains a number of cells. And these cells can be connected in series. Increases the voltage, and it can also be connected in parallel, which increases the capacity, or the amount of electricity generated. And electricity is essentially just the flow of electrons through a circuit, and the battery provides the energy that pushes the electrodes. So what causes the fire? Well, today's electric vehicles all seem to use lithium-ion batteries, basically. Some don't, but many do. And the batteries that are used in these vehicles have very high capacities, so they store large amounts of energy, and this is to allow driving ranges of hundreds of kilometers. And the combination of the different electrode materials found in electric vehicle batteries and the electrolyte allows this high energy density. However, the thing that makes them so effective is what makes them a greater hazard, because high energy batteries burn more effectively and create much hotter, much more dangerous fires. But what causes fires in electric vehicles? Well, in electric vehicles, most of the fires start from the battery itself in a process called thermal runaway. Now, fires can start from elsewhere, then spread to the battery, which then burns, but this is much less likely in most conditions, other than, say, you park in the middle of a forest fire or something where fire is spreading to the vehicle. But in most cases, if the fire is starting from your vehicle, then it's probably going to be starting from the battery. So what is thermal runaway? Well, thermal runaway is when internal temperature of the battery increases beyond a critical threshold, and then the components of the battery may become unstable and react to generate additional heat. And this will go in a cycle. So, causes of thermal runaway. Well, electrical abuse is one of them. So, if you charge it too much, charging the battery, overcharging the battery, or over-discharging it, where you're expending too much energy out of the battery beyond the manufacturer's recommendations, can cause problems with the battery, which then may pierce the separator and cause short circuits. Other things such as thermal abuse. So the battery likes the 20 to 40 degrees centigrade range. So if the temperature gets too hot, then you could cause the separator to melt, just decompose, burn, and this could then cause short circuits. And you could also cause the electrolytes to decompose, and then this would allow the anode and the cathode to come into contact. And at very cold temperatures, you can cause metallic dendrite formation, and then that could also pierce the separator, causing short circuits. Mechanical abuse. So external force on the battery can cause piercing, pinching or bending to the battery. That can then cause short circuits between the electrodes. And this can produce localized heating, which can then cause fire. So for this reason, batteries in electric vehicles are kept in very reinforced areas of the car to prevent, severely reduce the risk of damage to the battery. So something listed above can result in an increase in the internal temperature of a cell of the battery. And this can provide energy to start exothermic reactions that release more heat. You can also get the melting of the separator that then allows the two electrodes to contact via the electrolyte that was before separated, and then you get sparks. And this is internal short circuit. And then any heat released increases the temperature of the cell, which initiates additional chemical reactions, along with the sparking, which can generate extra heat, creating a temperature-heat reaction loop. And there's so much in the battery that can burn. So remember the high energy density we were talking about earlier? Well, the electrolyte is a flammable solvent. The separator is a combustible plastic, which is basically made of polymerized petrol. The packaging and the rest of the vehicle can be burnt as well. There's a lot of plastic in modern vehicles, say 100 to 200 kilograms of combustible plastics. But this isn't much different to internal combustion engine vehicles. They are also the same in this regard. So as the temperature increases, you also get an increase to the rate of reaction, which means more heat is released per unit time. And this is not a linear increase in rate of reaction with temperature, but an exponential one. So for every unit rise in temperature, the rate of reaction is multiplied. So you can end up with a rate of reaction hundreds of thousands of times greater than the rate at room temperature. So you just get this thermal runaway, as it's called, where a little bit of heat causes an increase in heat, a further increase in temperature, and then heat and then temperature, and then you get this effect where you've suddenly got very, very hot conditions where everything is on fire and everything is burning. And the large batteries and more energy-dense batteries can lead to larger fires because there's just more stuff to burn. And electric vehicles can have some very large and bad fires, as you need so many batteries to power them. So in the battery pack, there's just so many batteries, so many cells. So the high temperatures, the high pressures can lead to cell swelling, cell rupture, and fire and explosion. And also the heating can cause decomposition reactions of, say, the metal oxides and the electrodes that can produce oxygen. And oxygen is interesting because you wouldn't expect it to be in the battery. However, because the decomposition releases oxygen, it allows combustion reactions to occur. So fire, essentially. So this allows the burning of, say, the flammable solvent in the electrolyte, and also allows flammable gases that are produced, such as hydrogen, to be burnt. And because batteries are so energy dense, because the cells are packed so closely together, you can get thermal runaway from one cell, say the initial cell where the whole thing starts, to any neighbouring cells. And then eventually you could spread it to the whole battery, setting it all on fire. So as I say, the effect of the thermal runaway is characterised by its exponential increase of the temperature. And this allows temperatures in the battery to reach 2,000 to 3,000 degrees Celsius, which is higher than internal combustion engine fires. And for this reason, electric vehicle fires can be much harder to extinguish, as they just take so much more water to cool down to stop them reigniting. Take into account they also produce their own oxygen, so it's hard to smother oxygen away from it. So in an internal combustion engine fire, you can cool it down with water, but you can also expel oxygen through putting water on it. But if the battery is creating its own oxygen, then it can burn even underwater. Battery fires can also produce some toxic waste products that are released into the environment upon the burning and can be washed away during hosing. So, the battery itself contains heavy metals. There are solvents and hydrocarbons which are just not great for the environment if they get leached out there. And as well, the acids and bases within the batteries, often not great either, can also pose hazard for people trying to extinguish the fire. So, finally, in the statistics we were saying earlier, there weren't many cases of electric battery fires within electric vehicles. This is good, but why is this? Well, batteries have a lot of safety built into them. So within the cell, there are many safety measures that reduce the risk of thermal runaway. And this is just built into the whole system. So in the cell, there are devices such as pressure relief vents, which release pressure at high cell pressures. So if inside the cell you get this heating and increase in pressure, then you've got valves that just release this hot gas, and this prevents the whole cell exploding. Also, the opening of the pressure relief vents basically just shuts off the current in the battery. And you know the separators I was talking about earlier, that when they pierce, they short circuit the battery due to the touching of the anode and the cathode. Well, these these separators actually are built to shut down with temperature. So because the separators are porous, when the temperature increases a certain amount, you can actually get the sealing of these to prevent the transfer of ions through them, which prevents current. So at the large battery pack level, you have many other safety features built in. So the battery management system is the primary safety device, and this controls and prevents the charge of the battery. So it prevents overcharging, over discharging, and it basically operates the battery within its manufacturer's specifications. So it keeps it within its operating limits to prevent it overcharging or over discharging, and shuts off when something goes wrong. You've also got a thermal management system which maintains the temperature. As I said, 20 degrees to 40 degrees is what the battery likes. So if the cell's too hot, then it can cool down through cooling technologies through the battery. If it's too cold, then you've got external heating devices to raise the temperature of the battery. This is quite hard because the battery's so dense. It's hard to get the whole thing cooling efficiently and heating up efficiently when required, but it does effectively keep it within its operating temperature range, which prevents thermal runaway. So if a fire does get out of hand, it's important to be able to control these fires. And these fires are quite hard to treat because you've got burning of so many different things. You've got the burning of solid materials and textiles. You've got the burning of flammable liquids within the battery. You've got the burning of combustible gases, such as hydrogen, which has evolved in some reactions in the battery and thermal runaway. Fires involving metals. Fires involving electrical devices. So there's a lot of things that are on fire in this battery. And if you've looked at a fire extinguisher before, you'll see that fire extinguishers are usually treat a certain type of fire, say water on a paper and textiles fire, or carbon dioxide on electrical fire. But what if you've got all of these fires in combination? There has to be a way to effectively treat these fires if they do occur. So the fire suppression method should suppress lithium-ion battery fires and control the raise in temperature. This is critical because this raise in temperature is the thermal runaway. So you want to really reduce the temperature to reduce any chemical reactions that are going on. If you reduce them low enough, then it stops other chemical reactions from occurring, and then that reduces the temperature even more. So if it's not sufficiently cooled, then the thermal runaway will just continue again. So you cool it down like half, well, it's still enough energy to cause a burning of many things, which then raises the temperature again, which then allows the burning of more things because you've got more energy to burn other things that couldn't burn before, and then you're back where you started. So this is a major challenge. You've got to effectively cool the battery down. And this is why firefighters report using significant quantities of water to put out these fires, because they're just so hot and you have to get them properly cool to prevent them catching fire again. It seems that water is quite a good and cost-effective method to fight these fires. So water is very good at cooling because it's got high heat capacity. Essentially what that means is high amounts of energy is required to change the temperature of the water. So if you've got 1 kilogram of water, you might need a lot of energy to change its temperature. You've also got quite a high latent heat of vaporization. So when the water gets really hot, it evaporates, and on that evaporation, it just sucks in a load of energy that allows it to evaporate. And this effectively cools whatever's around it as well. So think sweat, you're running around, really sweaty, the sweat helps cool you off because it sucks up the heat during the high, it takes up a lot of heat energy. But of course water is flawed in some cases because you're dealing with battery chemicals, electricity. Water out of the tap conducts that electricity because the ions within it. So if you just shove a water jet straight at it, you could get electrocuted, which isn't great. But there are a few ways you can actually deploy this water. You don't just have to shoot it with a hose. Well, you can just apply a water jet, stream of water straight onto the burning material to provide cooling. But on live electrical equipment, you're basically just creating a wire of which you can get electrocuted. You could spray the water in like a sprinkling fashion, so like water sprinklers, using fine water droplets, because each water droplet is surrounded by air. Air is quite a good good insulator of electricity, really reduces the risk of electrocution. And there are plenty of other methods that I could go into here, but I won't because there are so many of them, and I'm pretty sure no one is listening anymore. I don't think anyone is here. So if you made it this far, well done. It may be by accident, I don't know. You could have fallen asleep, it's perfectly possible. However, there are plenty of papers looking into electric fires and batteries and how to effectively extinguish them. So if anyone is interested, I will link some in the episode's description. But if you are here purely for the interest in the content, then thank you very much for listening. I hope you enjoyed this episode. I know long-ish science episodes are not always easy to listen to. Hence why I think our Mario Kart episode may be one of the highest ranking episodes, even though it's got nothing to do with anything really important. I know maybe that's controversial, I don't know. But if you did get this far, then well done. Thank you for listening. Any feedback would be appreciated. I think you can leave comments on Spotify now. Not entirely sure about that, but you can email or you can Instagram us. The email is thecuriositymonkey1@gmail.com, and we're at thecuriositymonkey on Instagram. But if you're on Spotify or Google Podcasts or whatever it's called anymore, YouTube Music, then give us a rating. This helps the podcast. But thank you for listening, and see you in the next episode.